A microplate reader basically measures what's going on in your sample, in each well of the plate, as if you were performing a series of experiments without having to set up each one individually. Every process happening in the sample, whether biological or chemical, emits or absorbs a light signal. These light signals are then converted into electrical signals and quantified, giving you the results of your experiment in the form of numbers, different for each well of the plate. The light can be detected using one of many light detection modes, depending on the requirements of the assay used. The most popular modes are absorbance, fluorescence, and luminescence, and we will explain each in detail in further episodes of our series. Single-mode readers are small and economical, but they operate in one dedicated detection mode only. They are a perfect choice for narrow applications, such as measuring cell viability or DNA concentration. Multi-mode readers provide much more flexibility, as they operate in a few detection modes. They are ideal for labs with a wider range of applications, or those which are planning to expand their applications in the future. Plate readers utilize dedicated optical systems to send light to your sample and measure the emitted signal by a light detector. In most cases, the light of the desired wavelength must be selected, using either a filter or a monochromator. But how do they work? In filter instruments, the light passes through the selected filter, letting only a certain range of wavelengths reach the sample. Direct light path means minimal light loss, which results in higher sensitivity, making filter instruments ideal for labs performing only a limited number of assays, or those looking for maximum sensitivity in a specific wavelength. For higher flexibility, a monochromator instrument is a better choice. Here the light encounters a diffraction grating that splits into a spectrum. Then the light of the desired wavelength range is passed through a slit which controls the bandwidth that reaches the sample. A monochromator instrument lets you use any wavelength, making it a perfect choice for busy labs where each scientist is working with a different assay. Still can't decide? Tikon's Fusion Optics offers both, filters and monochromators in one instrument. The basis of fluorescence measurements lies in fluorescent molecules, called fluorophores, which, after excitation, emit light. Some molecules are naturally fluorescent, but most need to be tagged with fluorescent dyes. The light of a specific wavelength excites the fluorophores in the sample. After a very brief period, light is emitted from the molecule at a longer wavelength. This difference between the peak excitation and emission wavelengths is called the Stokes shift. The emitted light is measured by the PMT, an extremely sensitive light detector. The emitted light's intensity corresponds to the fluorophore concentration. Enhanced PMTs and Tikon's readers offer exceptional sensitivity. Unlike standard PMTs, which are optimized for the green range of around 500 nanometers, Tikon uses a PMT which is also sensitive in the red area of the visible spectrum. Fluorescence is used for a variety of common applications, including nucleic acid and protein quantification, but also for more advanced applications like monitoring cell proliferation and toxicity, as well as high-throughput applications such as drug discovery. Absorbance is one of the most commonly used detection modes in a plate reader. But what exactly are you measuring? Light of a specific wavelength is sent through the sample. and the detector measures the amount of light that has been transmitted. Absorbance is a logarithmic function of the transmission, and it's given as an optical density, known as OD. The more light a sample absorbs, the higher its OD value. Using the Beer-Lambert law, the concentration of the solution is calculated, where A stands for absorbance, D for the light path length, which depends on the sample volume in the well, and epsilon is the extinction coefficient, which is compound and wavelength specific. These basic principles make it possible to use the absorbance spectrum for many different applications, which highlights its versatility in your lab. For example, ELISAs use indicators that absorb light in the visible wavelength range. Cell growth is measured at 600 nanometers, OD 600, which prevents cell damage from UV light. Whereas for nucleic acids and protein quantification, you use UV wavelengths, 260 and 280 nanometers respectively. The 260 to 280 ratio can also assess nucleic acid purity in your sample. In luminescence, light is emitted by the sample as a result of a chemical reaction. No light source or excitation system is needed. The light produced is the result of a chemical reaction between the enzyme luciferase and a substrate. It is then measured by a photon-counting tube, a low-noise PMT, which can detect low signals with the highest sensitivity. Luminescence is commonly used for luciferase-based gene expression assays. ATP detection, or for monitoring protein-protein interactions. Different forms of luminescence reactions can be used. A flash reaction gives a very bright signal, but as it lasts for just a few seconds, it requires an automatic dispenser and injectors. A glow reaction emits a less intense but more stable signal, which can be measured for up to several hours. It is often used for ATP detection and quantification. A multicolor reaction allows for 2 or more luminescence signals coming from one well. It's commonly used for dual-color reporter in bread assays. Tigon's Microplate Reader utilizes a future-proof filter wheel system that enables virtually any multicolor luminescence assay.